It is my pleasure to introduce our second speaker of the afternoon, Charlotte Satchwell, who is his final year PhD student. And Charlotte's going to be telling us about applying geometric invariant theory to K-moduli problems.
Thank you very much, Simon. Thank you very much for listening to our talk today, and to Alistair and his useful organising. Okay, so to begin with, let's so if we consider our variety of hypersurface XD, which lives in weighted projective space. This is where our x value has weight A0, our y value has weight A1, Z A2, and A3. And then we have our weighted homogeneous polynomial FD of degree D. And our aim is to construct a compact moduli space of this. So for when we have our degree D is greater than the sum of our weights AI, then or we have D is equal to the sum of our weight AI, then yeah, that's already understood. However, when we have the degree is less than our weights, then we have this isn't sorted in all cases because we have problems with so our X may receive many automorphisms, which can cause problems with the moduli space. So how do we construct our moduli spaces? So the naive idea might be, so if we consider B equal to Cm as our space of coefficients, and we had our group G is equal to our automorphism group of our weighted projective space P. Then we might just take P and then quotient out P of B and then quotient out G. However, this causes problems, as I'm sure many of you in the room are aware, because it's not always an algebraic priority, which, yeah, not good. So instead, we turn to, so Mumford showed that if we have, if G is reductive, then we can use geometric invariant theory to show that there exists a semi-stable subset of V and the GIT quotient is a projective algebraic variety. Called the GIT quotient. And then so how do we determine what the semi-stable points are, or the stable points? We turn to so we then have the Hilbert-Mumford criterion. So the Hilbert-Mumford criterion helps us determine our semi-stable or our stable points. Now, for our case, we run into some problems because our automorphism group is not always reductive. So if we have our and this happens in our case when there exists a weight such that we can write it in terms of a sum of the other weights. So as in there exists an AI such that AI is equal to the sum of some sort of formulation of the other weights. And so an example of when this occurs is for the degree 100 case. So if we have x to the degree of 100 living in the 5, 19, 27, and 50, then we can see that well, 5 divides 50. So yeah, quite a straightforward one. And yeah, so we have a unipotent radical GA, and then this is generated by sending. So again, we have X, Y, Z, W. So we can send W to W plus A X to the 10. So our automorphism group now instead looks a bit like this. So here we have the general multiplicative group to the power of 4. Here's our unipotent. So this part of the this part of our automorphism group is the reductive part, and this is the unipotent radical. Here, our GM to the weights is just the sort of T to the, so for example, 5 times the identity matrix, for example, so it'd be like T to the 19, T to the 27, 50, and so on. Okay, so now for the moduli spaces, there are 2 problems. So problem 1, as I've already mentioned, is that it's non-reductive in some cases. So our solution for that is non-reductive GIT. And then problem 2 is so in algebraic geometry, we don't want the moduli to depend on the embedding. X in P. So our solution to that is K-moduli. I'm not going to give a full definition of the K-moduli. Instead, I'm just kind of going to give you a brief idea of what you can think of being like. So our K-moduli, MND, K, parameterizes all Fanos X with minus kx n equals d. Dimension here, the dimension of x is equal to n, and all x k polystable. Okay, so right, okay, so what do we mean by sort of K polystable? So it was so how do we sort of show K polystability? So I think it was mentioned briefly earlier, but this is related to Kähler-Einstein metrics, and that's sort of why we care about it. But yeah, so it was shown by Zhu and others. That if our so if we have a moduli nk is projective and has KLT singularities. In our case, we're quite fortunate, and because we're just working, we've got surfaces. Our KLT singularities are just equivalent to thinking of them as sort of quotient singularities. So for anyone that sort of
when you say it has KLT, is the projective moduli space with KLT similar?
Oh, sorry, no, the x.
The element of the moduli.
Yeah, sorry, the element of the it's projective. Should probably rewrite.
Just write x, we know what you
Yeah, x has KLT singularities. So for us, it's just quotient singularities. So for anyone who doesn't know what I mean by that, that's just BC squared quoted out by a finite group. And then we can define the alpha invariant to be alpha x is equal to the supremum of lambda such that x lambda d is log canonical. Again, in our case, that is also just equivalent to quotient singularities.
Well, not exactly.
Not.
Replacing log canonical of quotient singularities and taking the supremum is equivalent.
Oh yeah, sorry, yeah.
So
So you have to, when you take the supremum, it's equivalent, but not when you, if you don't take the supremum, it's not.
What is D here?
D is so D is for all D equal to the sum of AI DI, where DI the curve's equivalent to minus KX and AI is greater than 0. Right, so that's the alpha invariant, and this is what we use to show K polystability. So if in our case, if alpha x is greater than 2/3, then this implies that x is K polystable. Now, our examples, we're actually looking at the examples of x which are exceptional, and by exceptional, and this is just where alpha x is greater than 1. Why we look at the exceptional? So the exceptional is a finite, there are finite many families. they're exceptional. And if we assume that our sort of general element is quasi-smooth, then these are already classified by Chelpsoff. Sorry, did you have a...
Yeah, you need a group here, right? On the alpha, right? No.
No?
Yes.
Do you?
What? No.
Yes. Otherwise, it's case stable.
What are you talking about? You don't need a group to define a number.
No. The conclusion is K positive. It's not this alpha, right? You need some reductive subgroup in the homomorphism.
No. I think so. Your thing is larger or equal.
No. If it's larger, if it's larger or equal, it's going to be case stable. If it's written this way.
If it's larger than 2/3, it's okay. We talk about it later. I'm gonna stop her. She has very little time, so PhD student. So calm down.
Yeah.
It's gonna be okay. Well, I'll explain you later.
Okay. Yeah. So in our work, so we have that for all exceptional hypersurfaces of dimension 2 that are Q-Gorenstein rigid. Q-Gorenstein rigid singularities only. Don't worry too much if you don't know what that means. Whose moduli space we get from the GIT has dimension 1. Then we've shown that the GIT is isomorphic to the sort of the element of the K-moduli of degree D, so irreducible component. So I'll finish off with example of the degree 100 case, just sort of going through some of the calculations.
But does that mean that there's only like one polystable point here in
Yeah.
this theorem?
Yeah.
No.
Wait.
Dimension 1.
Yeah.
Oh no, sorry. It's
an orbit.
sorry lines.
Huh?
Is it an orbit or?
No. It's what I don't understand. What does the XD in brackets there?
It's the irreducible component that we're looking at for the K-moduli, because we haven't got the whole K-moduli, have we? It's just one.
Okay. So you don't mean it's isomorphic to XT, it's isomorphic to the reducible component in the moduli that contains XT. Okay.
Yeah, sorry.
Yeah, so it's one dimensional. The model is one dimensional.
Yeah, should I think of it as an S equivalence class? That's usually the notation for the S equivalence.
Yeah, I don't think this notation is just on that base. It's one dimensional component.
Yeah.
The reducible component. So there's no one, there's P1.
Yeah, exactly.
Yeah.
But you get like a single polystable point, right? That's the idea.
No? Get that one dimensional.
Yeah, fine. Yeah.
Okay, so back to the X100 example. So the general element will have a polynomial f defining it like this. And as I mentioned earlier, if you've got a non-reductive group, so we use non-reductive GIT, and this was this is from the sort of UHAT theorem, which is Betsy, Doran, Hawes, and Kerman, who is, I'm sure, giving a much better talk on this subject than me later. So BBH. This was the UHAT theorem, and this is basically the equivalent to the so this is what we used to sort of regain all of the stuff that we needed from the reductive GIT, and it ensures that a quotient exists. So this has some added assumptions. So one is that we need the weights to be adapted. And two, we need semi-stability to coincide with stability. On the interest of saving time, I probably won't go through those. So if we have so if we take our example, okay, I'll quickly skip ahead to the Hilbert-Mumford criterion. And this is a slight reformulation to the sort of like normal way. But this again is exactly the same as it's the same as the reductive. But yeah, again adapted by work by the same people. And so with respect to linearization, and assuming that you have assumption solved, then we have our elements in X are semi-stable if and only if 0 is in the Newton polytope G dot X. And so they're semi-stable if they're in the interior. The closure or G in G, and then they're stable if and only if they're in the interior. And then so I'll just sort of briefly say we sort of do this, we end up with our sort of our semi-stable set and our stable set, and stability coincides with semi-stability, and then we get one element which has a non-quasi-smooth, which is not quasi-smooth, and for that one we need to complete the alpha invariant to check that it's K-moduli stable, and then once we've done that, we know that we've got the K-moduli. But yeah, thank you very much for listening. Does anyone have any questions?
Does anyone have any questions? You're waiting to us. John?
Yep.
Where do you think the conventional one-dimensional component of the calculation or?
we've done all the dimension one, so I've sort of put that as because it's quite a nice sort of theory just to say we've done all dimension one. We've done a few of the higher dimensionals, but haven't completed like the whole list yet. So just sort of put dimension one because that'll be the sort of first paper that comes out, if that makes sense. But yeah, you could do it.
The case becomes more complicated because the moment the way you do it is you construct a GIT, which actually she didn't say, but the left hand side in GIT is not unique choice. There's a parameter that you have to choose, and depending on what you get, either one compactification or another, and not all of them, of course, are isomorphic because they're not isomorphic. Among them, on the right hand side is unique. So you go to dimension 2, or dimension 3, and so on. The complexity grows. So grows in the sense that you a priori don't know what the left hand side, which one is going to be the right one. You have more of them to consider, but also grows because assuming you are considering the right one, when you find the limits, you need to check that each of them are equally stable. When it's dimension 1, there's only one of them. And when it's dimension 2, there's a correlation, which can be done. It's not significantly harder. It can be done, but you know the amount of pages quickly grows exponentially over every dimension.
Why choose the alpha invariant, not like delta?
Yeah.
Easier?
So the reason why we chose the alpha invariant is because we were looking at the exceptionals to begin with, and for the exceptionals it needs to be greater than 1. We wanted to see if that would then correspond as like a following sort of like, so if it's exceptional to start, does that necessarily mean it would be exceptional after sort of thing? And so that's why we did the alpha invariant as opposed to the delta invariant on it.
So another motivation for it, so it's not clear that the limit should be exceptional.
Yeah, sure.
It is not actually, but in general, but it is in most of them, which depending on your view can be surprising. But exceptional is important because exceptionals you cannot have two very rational vibrations with special fibers. If the special fiber is exceptional, you cannot transform it to something else. Because the addition of the alpha invariants where the vibrations are isomorphic apart from one fiber, those fibers, the alpha invariants have to add up to at most 1. So if it's larger than 1, you cannot change for the peso vibrations.
Did you have a question? No? You had a question.
Yeah. Could you briefly explain why the U-hat assumptions hold for this problem?
Yeah, so it's kind of to do with you end up having, so you have a choice in sort of chambers that you can take, if that makes sense. And then you end up sort of I don't know how to do the answer. I don't know how briefly I could do it without boring everyone on whether I want to go for a break. But yes.
We do have a half-hour break in which you can explain.
So yeah.
All right. Shall we stop there for the moment then? Okay, let's thank Charles again.